Reference book is by author Houghton. Fundamental concept that I learnt on error control coding. Suppose you have a message of 2 bits. These 2-bit messages can be 4, and if we add a parity bit for error detection, we have valid code words which are counted to 4 due to even parity, and invalid code words will be these set because they are odd parity bits and they are not the valid code words according to even parity scheme. A 1-bit error in this bit code word will result in a invalid code word. There are, say, k equal to 2-bit message, 1 parity bit added, 3-bit code word. 3-bit code word has got 8 possible combinations listed in front of you. 4 of them are valid bit code words and 4 of them are invalid code words. A single bit error will, suppose this one 3-bit message which is embedded in a code word is sent, then if 1-bit error occurs, then it will end up here. Now, how to get this picture in a diagram? We can use n cube, in which the valid code words are inside the green circles and invalid code words are inside the red circles. From a valid code word, if 1-bit error occurs, we can go into 3 different error situations in which all 3 are actually not the code word set, they are the invalid code word set. From there, we don't know if we have to go here by changing 1 bit or we have to go by changing 1 bit, because when an error occurs, we don't know what was the original message sent. So a 1-bit error can cause problems, because if we change 1 bit from, let us say we send this message 000, it is a code word with even parity. If 1-bit error occurs, then either of these 3 nearest neighbors can result. When this happens, these 3 neighbors are in the error set code words, and in the error set code words, the 1-bit change results in 3 possibilities in the valid code word set. Now which bit changed, first, second, third, we don't know, because that's an error. To overcome this situation, a fundamental rule needs to be developed, and to do this, basic understanding is that when a 1-bit error occurs, then it should be at least 2 distance away from other valid code words. You can see this picture to understand this concept. If this is the message sent and 1-bit error occurs, then if it is distant 2 bits distant, 2-bit error distant from the next message or the nearest valid code word message, then 1-bit error can come back by changing 1 bit to a valid message, and 1-bit error by changing 1 bit in this scheme can make it reach another invalid set. So invalid to invalid means that 1-bit error was not corrected properly. So this minimum distance can help us correct 1-bit error. 1-bit error occurs, 1-bit error change seen both sides, you have to come this way. So this is the right decision. So 1-bit error can be corrected if the next message is 3 bits away. 1-bit error, 2-bit error, 3-bit away. So we have to keep the distance more than just 1 bit from error, that is 1 bit change, that is 2 bit. So 2 bits reach another valid code word, this will not help. What should we do? So let us reduce the number of messages so that red circles are present more. To do this, I have changed the diagram like this. Now, so see, only let us say our code word set, the valid code word set is only having these two code words. So these two code words are valid, all other are invalid. Now, 1 bit error reaches here, 2 bit error reaches there, and 3rd bit error will allow to reach the next valid code word. You can see this in this manner also, that in timeline when you have a 1 bit error you reach these erroneous bits. When you have 2 bit error, then you reach this message bit, and 3rd bit error will result in this. So let us say this is a simple system and we only suffer 1 bit error. 1 bit error will reach in either these three of the options, and from there the receiver can check. 1 bit change can make you reach there, which is not a valid code word, and 1 bit change can reach here also. So 1 bit change from 1 bit error reception can make you reach a erroneous code word, invalid code word, or a valid code word. So 1 bit error can be corrected back easily without any problem. So error detection and correction are now possible just because we have inserted a larger space, the larger bit space that has been, the bit hops that have been embedded inside. This is called minimum distance. It is a fundamental of orthogonal space, which is just the space between the valid code words. By putting more redundancy into the code word bits, these are redundant bits and these are the valid code words, we can correct 1 bit error. Now to generalize this, what we can do is we can infer that to correct 1 bit error we need to develop a minimum distance. What that must be? A 1 bit error say equal to variable t, we needed at least 3-bit distance. So this 3-bit distance can be generalized as 2t plus 1, which is the minimum distance that should be there to correct a 1-bit error. So this is our solution, and we are now confident that 1-bit error can be corrected by changing 1 bit. So if you have a visualization in 3D, you can see that this can go to 3 places, then further these can go to 2 places, then they can reach to the other code word. There is a sufficient space between the 2 valid code words, and 1-bit error can be corrected. So this is the single fundamental concept of error correction.